On a donc le plaisir d'accueillir Antoine Tilloy aujourd'hui, qui est en ce moment à l'école des mines, et qui va donc nous faire une conférence, je lis le titre, du lien entre les modèles de collapse non markoviens et la théorie de Broglie-Bohm. Donc je laisse la parole à Antoine. Merci Antoine.
Okay, I switch to English perhaps for for everyone. So thanks a lot for the invitation. My objective today is to present a recent result I obtained with Howard Wiseman, connecting two leading approaches to, two realistic approaches to the foundations of quantum mechanics. On one side, modern collapse models, and on the other side, the Broglie-Bohm theory. Let me first very quickly summarize the result in the introduction, and then the whole talk will have as purpose to clarify this equivalence that seems very counterintuitive at first. So we have two realistic reconstructions of quantum mechanics, apart from many worlds, so that are single world reconstruction. The first one is the Broglie-Bohm, and to simplify, we have a wave function evolving unitarily with the standard Schrödinger equation. This is where you get predictions from, and then you have the fact that particle moves according to a guiding law that you derive from the wave function. And this second part is more, if you like, the metaphysical aspect or the ontological content of the theory. It tells you how you derive clearly measurement results, for example. Another approach, objective collapse, again I will describe in much more detail how you construct such models, is you instead modify the evolution of the wave function with you add a small perturbation, nonlinear and noisy, to the Schrödinger equation. And this is like where you get the predictions from. And then what is real, like the predictions of the theory, are obtained from from psi itself, or from even the collapse event, so the noise itself. I will tell more about this. So these are completely different approaches philosophically and practically to the solution of the measurement problem in quantum mechanics. And what I want to show today is that there is a deep connection, in fact, between the two, and stronger than is usually believed. So there is a first weak inclusion that I have to say first that is very simple, in a way not always known but quite intuitive. And it says that if you take a collapse model of the continuous type that is reasonably generic on a certain system, say the universe, a standard model, then you can cook up a bass of harmonic oscillators and a unitary dynamic, so a Schrödinger evolution on the bigger system containing the bass, such that the two models are empirically indistinguishable. Okay, so if you have the collapse model on the system, it's empirically equivalent to something unitary, either interpreted with the Broglie-Bohm, many worlds, Copenhagen, or whatever, on S plus B. Okay, this part is, as we will see, fairly obvious or easy to derive. What I want to show is something stronger than this, ultimately, but it's already good to have in mind this connection. The strong inclusion is that if you take the same choice of bass, you can give the oscillators in the bass Bohmian positions. Okay, you just describe with Bohmian mechanics just the bass part of your system plus bass. And then you can show that the wave function of the collapse model on the system alone, is the same as the Bohmian wave function conditioned on the Bohmian particle position of the bass. And further, the noise that seems to drive the collapse model has exactly the same law as a linear function of these Bohmian positions. So we have that. I will clarify what I mean by ontologically here, but at a stronger layer than empirically, the really underlying dynamics of the collapse model on the system S is equivalent to the Broglie-Bohm applied to B alone, but on the whole, so unitary evolution on S plus B and the Broglie-Bohm on the bass, which then gives you a wave function standard one on the system. Okay, this is the stronger one, and this is, I would like to insist that there is no, as far as I know, shortcut to deriving it than doing a complicated computation. And it is not an obvious result. So if the second result looks obvious, there is probably some kind of misunderstanding somewhere. And the first one you can have a fairly easy intuition. The second one seems completely counterintuitive. After all, Broglie-Bohm is deterministic, collapse models are stochastic. How come we can have the same dynamics? I will try to clarify this in my presentation. Sorry, I think I forgot to explain this. I will start by explaining the very basic principle and the origin of collapse model. Then tell you more about the structure of collapse models and something I call the theorem of Gisin, which really strongly constrains what kind of models we can have. Then I will describe the more modern collapse model with colored noise, which are the one I connect with the Broglie-Bohm, and then show how through dilation and the Broglie-Bohmization, how I can get a connection between the two, actually just a real equivalence, and then discuss the implications of this result. Okay, so you see a large fraction of the talk is explaining really the historical construction of collapse models from the way I understand it, and what is to then really explain something that I think are misunderstood about their structure, and then which allows me to connect it with the Broglie-Bohm. Okay, let me start with the Girardi-Rimini-Weber as an instance, the simplest instance of collapse model. I just start maybe even more generally by the philosophy. Okay, and first, if you look at the literature, this has many names. Okay, so sometimes it's called model or program, and for collapse you can say reduction, collapse. Okay, or in French there are three options, and then objective, spontaneous, dynamical. All of this covers the same type of models. Unfortunately, I don't know how to say Shuya in English, but you have the Schrödinger equation, and then you add by hand a small perturbation that is noisy and nonlinear, and that essentially has the role of choosing the macroscopic branch of the wave function you're in. Okay, that is an objective collapse term. And H here doesn't have to be the simple Schrödinger Hamiltonian, it's whatever you want. It's typically the Hamiltonian of everything, okay, the Hamiltonian of the standard model. Even though in practice we can only deal fairly easily with relativistic approximations. And a priori it's ad hoc, but I certainly here don't want to justify that these models make sense or are interesting or anything. I just want to say what is just interesting at first sight is that it's possible to solve the measurement problem this way, that it is a viable way. And an instance of the Shuya is the GRW modification by Girardi, Rimini, and Weber. And so in this dynamics, you just think that everything evolves unitarily except every elementary instant of time dt with a very small probability lambda t, the particle in an ensemble of n particles collapses to a point x randomly. Actually, it doesn't exactly collapse to a point, it collapses to a certain envelope. So you have a certain superposition, then stochastically you collapse, and then you are multiplied by a Gaussian envelope that strongly narrows the wave function. And the probability of this collapse is given by the Born rule. So that's what gives the statistical law of this collapse. And in fact, this is crucial to making the theory viable. That is, you cannot choose any other probability distribution for these collapses for the theory to make sense, and we will see that in a few slides. So it's a very, very simple dynamics, and it's not the kind of dynamics I will consider. I will consider more modern versions that are continuous, where you don't have this kind of brutal collapse, but the philosophy is, I would say, very similar. Why does it work? Because why does it work? Maybe I should say rather, why is it not obviously falsified? Because if you take a very, very small rate of collapse, 10 minus 16 seconds, electrons almost never collapse. You will never see a single electron that you isolate or a single ion collapse. But a cat will localize instantly to a size of, at minimum, at most RC, the width of this Gaussian of collapse that can be made very small. So it's something that is completely negligible for small systems and that becomes huge if you have large systems. And in brief, this is a bit of a long story, but you can understand how you can derive sort of semi-rigorously the measurement postulate, everything we know about Copenhagen, by applying by studying the dynamics of the measurement apparatus, obeying such dynamics. And importantly, all the microscopic degrees of freedom you see in nature, like spin, photon, they don't collapse. They don't get definite measurement results because of their intrinsic dynamics, but because of the dynamics of the measurement apparatus, because it is the measurement apparatus that has this multiplication effect. Okay, so that's why, again, I'm not saying why you should believe in them, because I'm not sure I believe in them, probably I don't, but just want to show why they are not, how they solve the problem and why they are not obviously falsified. Of course, even if this collapse rate is weak, it still has consequences. Before the consequences, I forgot. I will first do the metaphysical part, the ontology. So now that we don't start from Copenhagen, we have to give an intuition for sort of what is real in the theory and what explains how, if we commit to some kind of strong form of realism, how we derive measurement results, the Born rule and everything from the dynamics of this model. And then you have a popular approach is to say just choose an ontology, so choose what is real in these models. And there are basically three approaches. The first, you just say the wave function itself, now that it has only a single branch, because this thing doesn't make Schrödinger cut. So you say the wave function now is believable as a real object. It doesn't have like these macroscopic branches, so I choose this. Or you can choose, but the wave function lives in configuration space. This creates actually an infinite literature of subtleties. And so you can make simpler, even though perhaps less aesthetic choices, where you take the mass density of all the particles. So instead of taking a field in configuration space, the wave function, you project that down to R3. And you get what people call a primitive ontology in that case, so something living in 3 dimensions. And then tables and shares are obtained from the coarse graining of this field. Okay. And the last option is to take these collapse events, the points where the wave function collapses, as the only thing that's real. It's a sort of extremist view. And there the world emerges from this kind of pointillist picture in space and time of all these flashes, very frequent. And then tables and chairs emerge as sort of, these pictures, but these are not dots that are stable in time, like atoms. They are really dots in space-time. They are just pure events. It's a choice that Bell hinted at, and that has the advantage of allowing very conveniently relativistic generalizations. Okay, it's very difficult to make objects like this have good relativistic properties, the first two. This one, while not easy, seems feasible. Okay, for the third one. And what I will say, the connection with Bohm I will draw will work on continuous generalization of the first one and the last one. This one there is no way to connect it with Bohm, as far as I know. Okay, now that I did the metaphysics, there are some empirical consequences of these models. The first one, which is the most natural one, is that if you start to interfere big things like furans furans it's still okay, but larger and larger macromolecules, you should expect at some point that interference fringes will stop. It turns out it's the neatest verification, but it's really not a stringent test, actually. Much better consequences are, unfortunately, indirect consequences. The fact that matter heats very slowly, but these models don't conserve energy. So these constant flashes, like a collapse of the wave function, inject energy. So matter, bulk matter, everything, table, chairs, they heat up very, very, very slowly. So it's completely impossible to see. But it could be seen if you had neutron stars that are super dense, so where the effect is strong, and where the surface to radiate is weak. Also, stuff vibrates, so even bulk matter weakly vibrates, and this you can test in the mirrors of gravitational wave interferometers. And finally, because of these collapses, matter, so some atoms can spontaneously emit X-rays for no reason. Okay, just when there is a flash. And basically, so for the first one, you have the experiments of markoviens that are good tests, even though again it's not a very stringent. For the second one, I particularly like neutron stars, but it's very biased because I worked on that at some point. And for the third, the mirrors of Lisa Pathfinder. And finally, the most stringent tests currently are germanium crystals under the mountains, where people just try to see if they will emit X-rays, and they don't, and so this gives bounds. And this gives us this white diamond of authorized parameter region. All the upper part is falsified by experiment. The lower part is not falsifiable, because you can always make the collapse weaker and weaker. It's philosophically useless, okay? Insufficient reduction. It means that if you take values lower than this, Schrödinger cats stay Schrödinger cats. They don't get projected. You still have many branches, macroscopic branches of the wave function. And in that case, you didn't win anything by buying this model. So, of course, this is absolutely not sharp here. You see that even the historical value proposed by JRW is right on the line. It barely localizes macroscopic stuff. And most likely this will be closed quickly. Okay, so there is, I don't think anyone believes these models will not be falsified, at least in their current versions. The first question I think that people have when you see such models is why? Why choose such a weird modification? That is at the same time stochastic, so in aesthetic, why do you add stochasticity? And why does it look like this? It seems there are zillions of ways to do it, and that Girardet, and Weber choose the ugliest one. And I think it's in 88, Weinberg probably thought the same, and he decided to introduce his own nonlinear modification of quantum mechanics that was much neater aesthetically. But then he hit something that, in fact, Nicolas Jean had published just before, to explain that the only nonlinear modifications of quantum mechanics, so if you add, okay, let me state actually what Jean said. If you make a nonlinear deterministic modification of the Schrödinger equation, you can always send signals faster than light. And it's very trivial to see. You consider Alice and Bob sharing an entangled pair, and because of this nonlinearity, they can see the difference between a between a true mixture, a statistical mixture, and an entangled state. So Bob can know if Alice measured or not her side. Bob gets information from the fact that Alice measured or not on her side. Whereas in standard quantum mechanics, there are correlations, but that cannot be used to send signals. So with any nonlinear linear modification of quantum mechanics, you can, by being smart enough, find a proper EPR pair such that by doing local measurements then on each side, you can use them as telegraphs. Okay. So this is not good. Okay, there are ways to exit it. You can abandon the Born rule, but then it's very difficult to extract any predictions from the formalism. Okay, there are ways to exit this, but I would say it's very strong, and when people propose models that avoid it, usually after a while you can prove that they don't work for some reason. Okay, so far it's not been avoided very conclusively, I would say. And actually it's much easier if you can verify this theorem. Okay, so make it such that you don't have such nonlinear modifications. But it's very easy to see that GRW is nonlinear. Okay, so it avoids it by being stochastic, and how so exactly is actually quite easy to see. So the crucial point is that in practice, if you do experiments, and you have to buy the fact that you can obtain the Born rule and all the formalism of quantum mechanics as a theorem in this approach. If you buy that from me, then in practice you only measure frequencies, say a certain, to simplify you could take POVMs, but say the expectation value of a projector, but it's also averaged over the randomness of these jumps, because you don't have primary access to these jumps. You only have access to these spontaneous collapses through the statistics that you see. So it's always averaged over the stochasticity. By E, I write the expectation value in the statistical sense. And so if you do the math, you realize that everything is actually, all the statistical predictions you can ever make about anything are always contained in the density matrix. So in fact, the stochastic state evolution empirically doesn't contain more information than the density matrix averaged over these jumps. Okay, all the falsifiable predictions. Of course, if you have the stochastic state, you can solve the measurement problem, you can do more stuff, you can explain how, give a sort of consistent metaphysical picture of the world, but you cannot say more empirically. And of course, the probabilities of the GRW model are chosen precisely such that the nonlinearity cancels. So when this evolution for psi is nonlinear, but once you average over the noise, the probability term cancels the nonlinearity in the normalization, and you get an equation that is linear. And thus you cannot send signals faster than light with GRW. So all I would say the standard apparatus of quantum mechanics is saved if you just modify the standard Schrödinger equation by this other deterministic equation, at least for the purposes of making predictions. And nowadays, every single collapse model that has been proposed has followed this strategy, so of having a linear collapse equation. I should say not every, because Franck has tried versions that don't exactly preserve it, that sort of weakly preserve it, but I would say in the standard collapse literature, people have done that. Okay, so far so good. Now let me go into more detail into how modern collapse models are built and really understand the sausage machine. So usually that's not what you want. You don't want to know what's inside the sausage because it's a bit disgusting, and here it's a bit the same. Okay, the construction of the modern collapse models is far less intuitive than it seems. If you read the papers, if you skim through the paper quickly, or if you listen to quick explanations of how they work. So again, what I will say in this presentation doesn't, strictly speaking, I will go back to this, doesn't apply to simple collapse models like GRW, but rather to the fancier modern improvements. Why were these fancier modern models introduced? To avoid falsification primarily, because with the white noise, with the strong Markovianity of these models, the energy injected by the flashes, by the jumps is so high that we believe that they will be quickly falsified. And these modern models have much milder empirical consequences. Okay, so let's try to build generic collapse models. What do we have? So we want to write a modification of the Schrödinger equation that is nonlinear and stochastic, because we now understand it's more or less necessary for things to collapse. And that is small and that maybe is smooth in a way, that has some memory, that is smooth enough that it disturbs a bit less the wave function than previous approaches like GRW. The first is that you want this to collapse to a certain basis that is reasonable. Okay, it's like position. You don't want the world to be in a single branch but in momentum space. And second, to satisfy, to not annoy Nicolas Gisin, you want the master equation obeyed by this, by the average density matrix, to be reasonable, to be linear, in fact to be completely positive trace preserving, which is what standard maps in quantum optics, for example, verify. So it's any reasonable map on a density matrix, if you want to preserve the probabilistic apparatus of quantum mechanics, will have this property. And so you want the same for your collapse model, but here it's not the trace over an unknown system, it's an average over the stochasticity that you introduce. And these are requirements that you put. And then now from that you try to see how does it constrain the function. Okay. And this is how you constrain this model. So you have a first, this is the linear equation that people have as starting point. The first term is the Hamiltonian. Then you add certain operators you want to collapse, these A's. They are the bases, the operators in which we collapse. Think of position. And in front of it, we put some noise. That's the natural term. We add some noise to drive the Schrödinger equation, and this is the noise that will enable collapse. This is what you like. This is what you have intuition for, and when people talk about it, they talk about these two terms. And then you have an absolutely horrible third term. That is a functional integral over all the past, and tells you basically, had the noise been different, how would the wave function have been different? It's very, very hard to have an intuition of what this term is doing, okay? It's a functional derivative with respect to the noise in the past. So this thing is not just non-Markovian because it's driven by a noise that is colored here. The non-Markovianity is much deeper than that. It's like the state depends on all its history. How do you get this term, actually? You start from this, and you say, and then you realize that it breaks linearity of the master equation instantly. And then you say, what is the easiest modification I could make to the equation such that Gisin is happy? And you get this. And you get this horrible term. And there is, in a way, no easier method to do it. And the easiest is already quite horrible, you see. This was actually found in quantum optics before collapse models. Okay, so as a way to find stochastic unravelings of master equation in quantum optics. But for reasons that are subtle, this is because this term is so complicated, this is as hard to simulate as a unitary evolution on the complete system plus Bass. You don't gain any simplification in the non-Markovian case. And then what you can do is once you have a legitimate application like this, it's known, it's a theorem that you can always dilate it on a bigger Hilbert space with a unitary evolution. So this is to show that the weak inclusion I mentioned is in fact quite trivial. Because we want reasonable master equations to preserve the bound rule upon averaging over the noise, it is guaranteed that there exists a dilation of this evolution on the bigger Hilbert space that will have the same master equation if we average over the hidden noise and does the same predictions. Okay, so this is the sort of the easy part. And what we will do next is construct this dilation explicitly. And then we'll prove more, we will prove more, of course, this equation. But this, importantly, this wave function here is not the full story. This is the easiest part of the story, believe it or not, of how you construct these models. The second step is that you realize that this state is actually not normalized. The norm evolves up or down. And to have a reasonable interpretation, this state should be normalized at all times. So what you do is you normalize it. You just say, okay, now I normalize the state. And then again, it breaks the linearity of the master equation if you normalize it carelessly. And then you do something that is even more complicated, is that you restore linearity by changing the law of the noise continuously in time. So initially the noise driving the equation was Gaussian, but when you take the expectation value of the state, the evolution for the density matrix is no longer linear. You say, I don't change the state, I change the average, the way I take averages by changing the law of the noise. And if you de-Gaussianize the noise, it's called cooking in the literature, so you cuisiner le bruit. With this non-Gaussian modification, that is again quite complicated. So if the noise is W, you act with a kernel on expectation value living in all the paths of the state. So it's a very non-Markovian complicated term that is in fact very hard to derive. So that this is the right form, very hard. No, it's a tricky 2-page computations with non-trivial theorems in stochastic calculus. So it's not an intuitive result. So I don't know, for example, a simple intuitive derivation of this result. Unfortunately, I just know to make the computation. Once you did the normalization of the state obtained from the horrible equations before, plus the continuous cooking of the time, basically you get your state, the state normalized and driven by this noise is the output. This is the dynamics of your collapse model. And this has all the good properties you would like. I don't write directly an equation on the final object because you can't. There is no good explicit equation on the last object. The way you construct it is through the 3 boxes, okay? You solve this, you do the normalization, the cooking, and then that there is no direct equation. Okay, in some simple cases, you can write perturbative expansions for this, but that's all there is. Okay. So general collapse models that sometimes people present it's just collapse model with colored noise. They are far more subtle than just putting colored noise in the Schrödinger equation. In fact, you have a memory term that is necessary for the consistency, for the internal consistency of things to preserve the linearity at the master equation level. But it's extremely counterintuitive what this term does. And second, you need to cook the noise, the Gaussian noise, in a way that is also very, first counterintuitive, and that has furthermore a derivation that is completely obscure. That seems miraculous in a way when you look at it. And these two features are very weird because first, if these terms are so weird, I mean, how would nature produce such weird terms that are just ensuring that the probability stays right? This really doesn't look dynamical, okay? We started from some constraints, we arrived at an equation that indeed solves those constraints, but it's quite awkward. Okay? And I would like to show that these two weirdness emerge naturally if you treat the bass in a Bohmian way. Not only naturally, but you get exactly the same. And this seems wrong, okay, but that's just the case. So I will try to explain it. Maybe also for people who want to think about this, I should say that I understand, and I think with Howard, we understand fairly well the result now, but still we need the computations. Like we need a special bass. It's probably not true in general, for example, that we could probably make more complicated collapse models and it would not hold. It really requires this peculiar structure, and it seems like it's really a contingent result, that it's not true for more general principles. And so probably some intuition about how to prove something more general and with relying less on the specifics of the computations would be useful. Okay, in the Broglie-Bohm equivalent, this we will show is equivalent to a simple conditioning on Bohmian positions. And this is equivalent to the guiding law for the positions of the particles. Okay, let me now move to this part. Okay, so my first objective is to find a bass to construct explicitly the dilation. So find a bass such that when I take the trace over the bass of the complete state, I get something that is equivalent to averaging over the noise in the collapse case. Okay. This will be my ultimately later. This will be my Bohm side. This will be my collapse side. And now I'm interested in the empirical equivalence. Okay, so that I imagine there is a dark sector, if you want, in nature, a hidden bass of oscillators that can be probed only through its interaction with normal matter. And so you can trace over this bass, and I want to show that it's the same as averaging over the noise in the collapse part. And this is actually fairly easy to do. So, okay, here I apologize that you have to trust me in a way, because otherwise I will do tedious derivations. The solution is classical, actually it's a textbook one. You introduce a continuum of harmonic oscillators. So it's not a very parsimonious bass, okay? I have a continuum of harmonic oscillators with a continuum of frequencies. And I have one continuum of harmonic oscillator per operator I'm collapsing. Okay, so if I have just X, I have one infinity, or otherwise I have more. I define the standard Hamiltonian for the oscillator, that they oscillate at frequency omega or minus omega. And then I take this peculiar coupling Hamiltonian, I couple them to the momentum of the oscillators with some coefficient that I can choose that depends on the oscillator number and its frequency. And then if I choose carefully these numbers here such that this object is the same as the 2-point function of the noise, okay, this is a 2-point correlation function of the noise of the collapse model, D. If I take it equal to this function of the bass coupling, then I can show that these are the master equations you obtain by tracing on one side of our stochastic averaging are exactly the same. And this is proved by Vick's theorem. And it's basically because taking expectation value of Gaussian noise is equivalent to averaging over quantum harmonic oscillators. Okay. So this shows that if I choose this bass, I show explicitly the Hamiltonian to show that it's not a particularly weird Hamiltonian. It's a fairly standard Hamiltonian. Okay, so this, if I take this choice of bass Hamiltonian and coupling of the bass to the system, then tracing over this bass is just the same as the initial collapse model with its complicated memory term. Okay, so this is the weak equivalent. This is actually fairly obvious. I could have just stayed at the level of there exists a dilation. I did more than that. I constructed an explicit dilation that does it. But we can do more. Okay, I have some slides that are technical subtleties that I have to say, to not say something that is brutally wrong, but that I think are not so important, so I will pass fast. In fact, what I showed just previously is not the exactly right basis of harmonic oscillator. We have to do first go into a rotating basis for them, and second, we have to do a change of variable taking new oscillator variables. Okay, these are, I think, technical subtleties that you can probably forget about. I could have written everything directly in this basis. It's just in that case the Hamiltonian is more complicated. But for the equivalence to hold, I will need to do Bohmian mechanics in this basis of oscillators, which is one that is less natural. Okay, but this is the same bus. It's just a canonical change of variable, and the new variables have also canonical commutation relations. So they are also acceptable harmonic oscillators. I could have started with it. Okay, now let's do the Broglie-Bohm treatment of the bus. The first step is we take the system, the state of the system on the complete bus plus, okay, this is bad to have called it system. Okay, the extended system, and you just fix the positions of the bus. I just, if you want, project to certain fixed positions. I fix the values x in the wave function to arbitrary values. And now what I get is a wave function on the S only. Okay, if I fix the function of that. So in wave function representation, it's like this. I have this new wave function that is with fixed bus particle position. Now it's a state of the system. This is just the full one with fixed here. Or you can write that in bracket form. Just saying I project on the bus particle position on the left, and this gives me now a state living in the restricted original Hilbert space. And you just now do something that may seem weird, and you try to look at the dynamics of this state. You can write the dynamics of this conditional state, and what you realize it obeys the same differential equation at the linear state for the collapse model. But the noise, and you have a connection. What appears as W, okay, there is no noise in this model. The dynamics is the same if I identify this function of the particle position and I say this is the same as the noise. Okay, so I get exactly the same equation as before, where instead of W, I have W tilde equals this, that is a function of the particle position, a linear function of the particle positions. Okay, so this conditional wave function of Bohmian mechanics with fixed particle position, a rather weird object, obeys the same equation as the linear collapse equation of a non-Markovian collapse model, provided, of course, I say that this W is the same as the other, which is not the case a priori. Second observation, because, okay, it's something that is crucial, this object is deterministic, okay? This is fixed. Okay, like, so if you know this, you fix them. Now this evolves with time because they are cosine and stuff. It's a Fourier transform, but this is given. This is known at once. You know the x's. You know it's a deterministic function of the x's. Whereas the noise of the collapse model is random a priori. But the equivalence of the two comes from the fact that if initially the extended system is in a product state, where the bus is in its Fock vacuum, so the no excitation in the oscillators, you think this is like you take it as the initial condition of the universe, if you like, and then you take that the positions of the bus are taken randomly with the Born rule, and this is typically what you do in Bohmian mechanics because they are not knowable, and the Born rule is the typical distribution for this in the sense that, and then it is equivalent, it's preserved, and this is the one you obtain also at equilibrium. So now, in Bohmian mechanics, we can't know the position of the oscillators. The best we can know is that they were drawn initially with the Born rule. And now we look at the statistics of this object. If these oscillator positions were drawn with the Born rule. And this statistics is the same as the one of the noise of the collapse model. Okay, this is probably one of the most subtle parts. So, Bohmian mechanics is deterministic. Of course, I fixed, they are not even evolving here. I just fixed positions. But I'm saying if these positions were drawn initially from the Born rule of the initial state, then it's actually this object exactly has the same statistics as the noise of the collapse model. What I'm saying is that empirically you cannot distinguish if randomness is progressively revealed in a noise field, or if everything is fixed at the beginning of time and then revealed through a Fourier transform of these unknown modes, because you cannot know them because they were thrown randomly at the initial time. Philosophically it looks very different, but really there is no difference in the statistics in what you could observe, and even more strongly, even if you were at a supernatural knowledge going beyond what we can measure, and even a knowledge at the metaphysical level of seeing the trajectories of these particles and of the world, you could not see a difference between the two. It's, as I will say later, it's really a nomological difference. It's a difference in the way the law is specified, not a difference in the actual dynamics of the ontology or of the hidden variable. Okay, so these observations are still at the level of the linear dynamics. Okay, I'm showing that if I fix, there is nothing Bohmian yet actually. I'm just saying I take them fixed, and then I get that the wave function evolve, the conditional wave function on this side evolves the same way as the Colas model wave function, and that the thing, a certain functional of the particle position has the same statistic as the noise, and it's nice because it appears in the same place in the equation, so that's what we would like. And then the second step is to do something slightly more evolved, is now say, okay, now I don't condition on fixed positions of the bass, but I let these positions I condition on evolve with the Bohmian dynamics. I do one thing, they were static before, now I evolve them with the Bohmian rule for how you make the hidden variable position evolve. So instead of conditioning on fixed xb, I condition on xb of t now. This xb of t is evolving. And with the standard Bohmian rule, I will give it in the next slide, but that's the standard evolution for how, basically there is a general prescription how to find the Bohmian trajectory of anything, not even just position, not even just a single position. But basically Bohmian mechanics gives you a way to find a velocity field generically, and that if you evolve particles along this velocity field, this is like the standard Bohmian trajectory. In the Bohmian literature, in the Broglie-Bohm literature, this is called the conditional wave function. Okay, this is just the standard Bohmian conditional wave function. I take a lot of time to explain how it's defined because sometimes there are still confusion about what it actually means, the conditional wave function in Bohm mechanics. This is very simple. Okay, there is no tracing over anything. Okay, I'm just fixing the particle of the bass to their Bohmian values in the global wave function. And this gives me a wave function on the system itself, but that evolves with an additional time dependence coming from the fact that I condition on new positions at each step. Observation 3, that is actually non-trivial, that requires the computations basically, is that this new field, you can define the same field as before, is obtained from the original field with the same non-trivial transformation as the one linking the original noise to the Cook noise. So doing this, going from static Bohmian positions to moving Bohmian position, evolving according to the standard Bohmian guiding law, is the same as going from the Gaussian noise to the Cook noise that preserves probabilities. Again, this comes from a computation that if the bass were not linearly coupled, it would not work. If the bass had anharmonicity in its proper Hamiltonian, it wouldn't work. So it seems quite contingent, but that's what we have. And now, if you put these three, technical slide, if you are worried about how you take, I don't want to spend too much time on this, just there is a well-defined prescription for how you take the velocity field in a general theory where the Hilbert space is complicated, and that just extends the standard Bohmian rule where you guide with the imaginary part of the gradient. Okay. This is, what I'm using is just the standard guiding rule, except you have to take a more general form, typically to include spins, things like that. But that's there is nothing weird is hidden under the carpet here. Okay, so now let me conclude with this treatment of the bass, and then I will do a few more observations. And this is the most verbose slide where I try to summarize this point. Is that so we take the wave function. The first observation was we take the wave function on the system plus bass. We fix the particle of the bass this gives the same dynamics as the linear equation for the collapse models, provided you accept that this kind of field function of the particles has the same value as the noise. Second point is we show that in fact these two objects have the same stochastic law. Okay, here there is no tilde for the noise. Then we show that indeed these objects have the same law, in fact. And then the third step is going from the linear to the nonlinear case, so introducing the normalization plus the cooking of the noise, and then this is where the Bohmianity enters. Okay, this is really where Bohmian mechanics is the tool that connects the two. We have to evolve the Bohmian position, and this gives exactly the cooking, with a standard Bohmian prescription for how to evolve. You put everything together, you get indeed that the wave function obtained by fixing the position of the bass to their Bohmian value, to their real-time Bohmian value, is a stochastic process that has the same law as the wave function of the collapse model. These are stochastic processes with exactly the same law. So if you are to plot trajectory on the computer for a reduced model, and you showed me trajectories, zillions of them, you couldn't see the difference. The equivalence is not at the level of averages of trajectories. Even the trajectories themselves are undistinguishable statistically. And then I mentioned the second step, which is sort of included in the first, which is the law of the field, these linear functions of the position, is the same as the law of the noise in the complete collapse model. I mentioned this is because sometimes people build the primitive ontology of collapse models from the noise field itself. And if I want to claim that they are sort of ontologically the same, I need to show that even with this other choice of primitive ontology, I have the inclusion. So if you say that what is real is this collapsing wave function of the system, then the first point is enough. If you want to go to other primitive ontologies, the second point is necessary, but fortunately both are true. For the mass density ontology, I don't know. The object certainly exists in Bohmian mechanics, it's just not a natural one, I would say. It's just, I don't think the Bohmian equivalent, which we can fairly easily define, because as I said, the states are the same. So every beable you build from the state itself will be the same in the two theories. It's just that as far as I know, this beable has not been introduced on the Bohmian side. Let me discuss briefly, it's a sort of introduction for the following discussion. First, I want to discuss the first implication because I think it's insufficiently presented. Okay, the trivial one, that it's empirically the same to have a bass or to have a collapse model. Sometimes people say that collapse models make predictions that are different from standard quantum mechanics. And this is incorrect. This is not true. The predictions of collapse models differ from a specific instantiation of quantum mechanics with a choice of Hamiltonian and choice of Hilbert space. In fact, they differ from the standard model. But they are not distinguishable from the standard model plus a dark sector hidden from us. Okay, so if we ever see results that are compatible with collapse models in experiments, you could still defend many worlds and say, no, but there is just this extra Hilbert space. We still have the superposition in this complete Hilbert space. This is empirically indistinguishable. Of course, collapse models typically lead to baths that are weird and that we don't think could be reasonable fundamental quantum field theories, but this is a different type of objection. Second, sometimes people say that collapse models introduce a randomness, a very specific randomness that has specific empirical consequences. And that, of course, this is included in the first point in a way, but I want to insist on this. This randomness of collapse models is not empirically distinguishable from a standard quantum randomness that you get from degrees of freedom that you don't know. And that's why it's so hard and why, in fact, this has a very practical application if you want to test these models, is that there are lots of papers that start from the nonlinear equation for these models that are typically complicated. Extracting predictions from them is complicated. But in fact, it's useless. At the end of the day, every prediction will be contained in the master equation that is much simpler. And so there is no need to use these nonlinear equations for predictions for experiments. They are useful to understand how it solves the measurement problem. And last point, the collapse models then bring nothing to foundation, and this is of course not true because they do solve the measurement problem. That's then you can discuss if it's a nice way or in a nice way or not, but I think this is undisputable that they solve it. Then is the solution better than others? That I don't want to claim anything, but I think it's undisputable that it works. Then the question is the price fair? Okay, this is for the empirical side. For the more ontological side, okay, what is crazy, and I think is maybe not so intuitive. Of course, after the fact, maybe it's intuitive, but that some random and deterministic dynamics can be identical. Okay, by that I mean that the only difference is nomological in the way the law is written. So for those who are familiar with probability theory, the stochastic processes are really the same, it's just their filtration is different. So the way information is released is different. But their trajectories are the same in law, taken globally. The way we can know information about them is not the same. Okay. Then I think that for collapse models that are colored, dynamics is clearly more intuitive from the Bohmian side. The Bohmian story I gave you is not completely trivial, but it's fairly simple to understand how you would define this collapsing wave function. On the collapse model it relies on tricky derivations that are quite counterintuitive. And now we understand why, because these derivations are incorporating into this complicated memory term all the unitary evolution of this hidden bus. And that's why it's so complicated, and that's why there is no simplification possible. And so probably we should restrict collapse models to simple Markovian ones like GRW that have jumps, and for which the kind of treatment I did can still be done, but then it becomes completely trivial in a way that is, the memory term is 0 for these models, so I can still construct a Bohmian version that is completely trivial, and then the role of the Bohmian particle is just to be an external source of classical noise, which is something without much interest. So in that case, the Bohmian, I would say the collapse model is preferable. I think this is also good empirically. Like empirically, it makes no sense to make these collapse models more and more complicated to avoid falsification. But this is another argument to criticize this excessive generalization. Something I find interesting is to apply the same kind of constructions to existing baths like photons. And so you can, in this context, you see that something that people have done in the past, so doing partial de Broglie-Bohm descriptions of systems of fermions coupled to bosons, for example, because some approaches of Bohmian mechanics are much easier to do with fermions, some others are easier with bosons. In that case, you just Bohmianize one side. Typically, for example, if you use fields, you Bohmianize the bosons. And you keep the fermions without hidden variable. And this is strictly equivalent to what we did here, if you do that. And then you can see it as a collapse model on the fermionic side. This also gives a fairly good intuitive understanding, in that case better I think on the collapse model side, of why these approaches solve the measurement problem. That is why tracing away the bosons in nature, describing just the bosonic part of the standard model in Bohmian terms is sufficient to solve the measurement problem. And this is the conclusion of the conclusion, and sort of the take-home message from my talk is that, okay, we have two approaches, two reconstruction of quantum mechanics that are realistic and that are single world, that try to have these two features together, that give I don't think it's a criticism, say a naive realism, but I am naive, I like naive realism, naive realistic picture of the world, and they avoid many worlds. But it turns out you start from two different philosophies, try to make something completely different, and you end up in a hidden way on the same type of dynamics with a guiding law. And this weird cooking of the noise, we realize it's just a guiding law in disguise. And this brings the question of, can we do differently? So is there a way to construct realistic single world approaches to quantum mechanics that don't rely on such guiding laws in a hidden way? And there are some approaches taking boundaries at finite times and stuff, but usually they are typically global approaches, not dynamical. So where you give yourself the whole history of the universe and then typically condition on the final time to pick backward trajectory. It's an open question to know if it's possible to do it dynamically. But at least with Howard, we think we showed quite convincingly that for two leading ways of doing it that are supposedly very different, in fact, all the toolbox, all the machinery making them work is identical. Okay, so I stop here and thank you very much for your attention.
So we can switch to questions. Michel?
Well, but first of all, thank you very much for this talk, which was amazingly clear and putting exactly the emphasis on the right issues to make a philosophical decision about these issues. So even though I don't share at all your taste for naive realism, I think that your talk makes very clear the stakes and then allows us to choose. So one point I noticed is the amazing difficulty and complexity of the process to adjust the random term in order to avoid, for instance, falling into Gisin's theorem and falling into discrepancies with quantum mechanics. And so the first point I think is what is the motivation to do that with all this complexity, just to fall into something that you can call an ontology. But then, if you see what you exposed, you see that the ontology is not unique. There are several. There is this ontology of wave function, the ontology of density of matter, just by the way, just the same two ontologies as Schrödinger in 1926. Then, and you have all the other ontologies, including the ontologies of Bohm, which are not unique either.
Yeah, sure.
So, Bernard d'Espagna, since we are in this seminar which was created by Bernard d'Espagna, would have said, in this case, that proves that you cannot select out of arguments from quantum mechanics or its extensions. You cannot choose one unique ontology. Therefore, it's, according to him, it would have been a proof that you cannot give one ontology of quantum mechanics.
But I disagree with the second implication.
And therefore, he would have said, therefore, that means that with quantum mechanics, you can only have a negative approach of reality that he would have called veiled reality. So, from his standpoint, your talk would have been a sort of reductio ad absurdum of standard realism, and maybe an inclination to what is very subtle form of realism, which is called veiled realism.
Okay, so I agree with the first part, that I 100% agree that there is no way, the ontology is always underspecified by the empirical content. So I fully agree, it's not even proper to quantum mechanics, it's just particularly pregnant in quantum mechanics. It's obvious we have ontologies that are, maybe you disagree, but fairly reasonable, or two different ones that are as reasonable and compatible, whereas typically if we look at the same thing in classical physics, usually one is clearly more reasonable than the other. You can have an ontology of point particles, or think that they are angels making weird stuff that makes stuff happen, but in that case the angel one is really weird. Okay. But I really, so this shows that the ensemble of possible naive realities or ontologies is large, given what we have, but I don't get the implication that it means none is possible. Actually, we showed the exact opposite, that many are possible, they come with costs, and we can't decide. At the end of the day, why I dislike the kind of anti-realism that comes from saying that is that we are saying things like, this shows that, something that I think is logically not correct, that this shows that there is no possible ontology. This is not the case, there are many possible. Then this can show this embarrassment of riches, can say, okay, maybe the program from an epistemological point of view is maybe not worth too much time, or that's a different point. So I still think in that case it's worthwhile. For my own research, it's been very helpful to construct semi-classical models in gravity, to have this collapse models construction, because they allowed extensions of the theory that were completely unthinkable within standard quantum mechanics, and that solved in fact open problems, things that people thought were not possible. And I think that's really the way at least the realists should go in foundation, that is to really try to probe things that are easier with these approaches, or in the same way for Bohmian mechanics, people are now trying arrival time distributions. This may not work actually, but it's good to try. So I followed Espana on the first, not on the second.
Just a little remark. Your answer is very interesting, but from my point of view, I would say this is perfectly okay. But in this case, you could just use this kind of model as a heuristic, not taking it seriously as a real description of the world. But this works. This also works for your issues.
But I like the fact that they are possible.
Yes.
But no, I'm fine. I think then the question is whether or not they are good heuristics in practice is different. I'm in this weird situation, okay, where I dislike. I love it here, but I dislike. Personally, okay, I don't have a strong argument here. I don't want to make one, but I'm not a big fan of Manuel from because of the way, because it doesn't seem parsimonious. It's sure it's parsimonious on the equation, but not so much ontologically for me, at least. On the other hand, I find it an extremely powerful intuition pump. I think it's what everyone has in their mind when they do quantum information or quantum computing. We think about it this way. So, and clearly, it's a much better intuition pump than others. Probably I would say even Bohmian mechanics or that I like, or so it's complicated. Like I'm not that's why I don't really defend one of these approaches. I think they have merits, and they have it's a different notion of a bit negative theology than the one you mentioned, but what I like with these approaches, Bohm included, collapse model included, they're allowed to criticize a lot of misconception about the theory that are, when people say generalities about the theory. For example, quantum mechanics shows for sure that the world is intrinsically random or things like that. You can qualify the statement and say, for example, there is a deterministic version where it's just in the initial condition, it comes with drawbacks, whatever, but you have to qualify that. So I think this is the main advantage of these approaches, also from a pedagogical point of view.
Thank you for the talk, but I cannot accept your thesis. I think technically you get a correct, you get results which are not, which are okay, because you assumed kind of infinite baths.
Yeah.
Now, and in principle, our theory is supposed to work even if our world is finite.
No.
No?
I mean, no, but quantum field theory is infinite even in a finite volume.
No, but if the energy, no,
I agree with that. Okay, but I think this is really a technical aspect to make the connection simpler, that the bath energy is potentially infinite. I agree with that. I agree. This is a simplification.
So, but the point is that usually people say that the Everett, many words, equivalent to Bohm, and that's not equivalent to collapse.
Mm-hmm.
And there is a basic experiment which distinguishes between Bohm, let's forget about Everett, you don't like it, and Bohm and collapse. Mm-hmm. You send a single particle on a beam splitter and you put a detector. And your detector is kind of not so big, but big enough so your GRW or your collapse or Philip Pearl method or any kind of collapse theory causes a collapse. And then you spend $10 million for technology which undo the measurement and send everything back. Mm-hmm. So if Bohm is correct, then the particle will go back into the source. If collapse theory is correct, the particle will have 50% chance to go into the source. Yeah, so you repeat this experiment many times and you can distinguish between Bohm and collapse theory.
You distinguish Bohm on the standard model, versus collapse models. And that is, I agree, is distinguishable. Now, if you do the same experiments with Bohm and a weak coupling to a hidden gravitonic bath, for example, that leaks away information, then Bohm becomes empirically equivalent to collapse. I'm just saying that you cannot exclude an extra dynamical sector in the theory. And then you will get back to the same result, that you leak information away into this hidden sector in a way that is empirically indistinguishable from the noise collapse models make.
So if I understand then correctly, then maybe what I started, then maybe you had to specify it very, maybe more clearly in the beginning. You say, if we consider theory with infinite random elements, then Bohm will be indistinguishable from collapse. But if the whole idea of Bohm and people who like Bohm is because it's deterministic theory when we can consider the world finite and we know everything. If we know everything, we can analyze all kinds of experiments, realistic trajectories, all kind of Wigner-Friend experiment. We can analyze and see that they're different, that they might differ from Copenhagen, collapse, GRW, and other stories. So if you by hand and random element into Bohm, then it's not surprising that you'll get the same result. I don't think you need to make more calculations. The whole Bohmians like it, maybe not the Bohm himself. Bohm never considered as a final theory. It's just kind of an element to go further. But the majority of Bohmians today see it as a possibility for a very nice finite theory, which is deterministic, and deterministic theory is better than non-deterministic theory. So in the moment you add random elements there, then it's not of interest that you'll show that it's equivalent to a theory where it's random is part of the basic principle.
No, but I don't add anything random, first. Second point is, I make the exact opposite point. So, in a way, I criticize collapse models here and in favor of Bohm. I show that collapse models are reducible to a Bohmian description. My point is not to say that you should make Bohm random. It's really the other way. And I don't say anything you should do, actually. It's more like the connection. But this is an important point, that if there is a sector that typically couples like gravity and that is quantum on the Bohmian side, you will never be able to tell the difference with a collapse model. This thing, if you have interaction you cannot shield yourself from, typically baths that will only leak, it is impossible to distinguish from the effect of a collapse model. The Hamiltonian I constructed is a reasonable one. It's not more infinite. In fact, it's less infinite than the typical Hamiltonians in quantum field theory. So, I
understand, but again, maybe we come from different motivation.
Yeah, sure.
Most of people who work on foundations of quantum mechanics, they do have hopes that maybe it will help to move quantum gravity, which is nowhere now today, by whatever. But the 99% of the task is to solve measurement problem. And then they consider a finite situation in in my room, when I look on all kinds of things. If I use any kind of quantum simple experiment, I'm in trouble. There is a tension between equations and what I see. And this is what all this Bohm, GRW, many words, consistent histories, Mermin, you can go, there are tens of them. And this is what they want to solve. It's maybe in the end, if they might also help something else. They do not start with gravity and field theory and whatever. We want to solve the measurement problem. And the measurement problem is solved differently by Bohm and collapse, very different. Yes. You make an experiment which is reversible. It's reversible for Bohm and it's not reversible for collapse. So they're absolutely different.
Yes, okay, I won't argue with that. I disagree, but I don't want to argue more.
Is there any other question? No, I have perhaps one naive question. You say that at the end, a stochastic process and a deterministic process are indistinguishable, because
With qualify.
yeah, one of your side says something like that. So my question is, what does that mean in view of the way we know now how to define random? It's not directly related to quantum mechanics, what I say. Of course, you know that there is the now accepted definition of random coming from Chaitin, and is a definition that applies especially on discrete things, and it's difficult to extend that to the continuous variables. But if we forget about that, then what you say, and it's interesting, but I'm trying to understand what that means. You say that you have on one side a stochastic process, okay, and we can think that it is intrinsically random. Do you agree with that or not? In your mind, do you agree on the fact that you can consider a stochastic process that is intrinsically random? Yeah. Okay. Then what you show is that you can collapse it on a deterministic
Okay, but this is
thing.
This is in a way in this particular example, this is quite non-trivial. I just want to say that in general, it's completely obvious. Imagine imagine a full Brownian motion evolving, okay, or a stock price. Imagine now you consider that nature, God, or whatever. Okay, I don't want to take too many risks on this, but just knows beforehand the trajectory. Okay.
But
just at the initial time,
yeah,
it was stored somewhere, or whatever.
No, that's the problem for defining random.
But this is
the
different.
definition of random.
There is no way to make any distinction between the two.
The usual definition of random is that you have no algorithm that helps you to compute.
But here
things.
it's the same. Okay, here it would be random for
So,
this algorithm.
so if you are a deterministic process, that means that you have a rule, okay? And if you have a rule, you have an algorithm that helps to compute the evolution. Okay, the
Yes.
dynamics. Okay. By definition of what we call today randomness, it is that there is no rule like that. I agree that I'm doing a sort of perhaps bad extension, because you know the Chaitin complexity.
Complexity theory, yeah.
Okay, so the algorithmic complexity is a concept that applies correctly to discrete mathematics, not to continuous one. So I just make an extension.
I'm not familiar enough with complexity.
So the definition of random that has been given by Chaitin in algorithmic complexity is that a chain of bits is random when you have no program able to compute these chains that is lower than the chain. Okay? And that's the today accepted definition of random for chains of bits. And I admit that a chain of bits is not a continuous one. So I extend something, perhaps it's not totally authorized. But if you forget about the fact that the distinction between discreteness and continuous variables, then in principle, if you have something that is random, you cannot have any algorithm allowing you to compute it. And when you collapse a stochastic process that is really random to a deterministic process, then you seem to do that thing. And I would like to understand how it's possible.
Because in the continuum you can encode an infinite amount of information in the initial condition. That's a point Nicolas Gisin has made a lot, actually. So once you work with real numbers, they hold an infinite amount of information, and in the initial condition you can encode everything.
That probably comes from the fact that you cannot apply the definition which is for discrete numbers to real numbers. And the extension of the notion of randomness to real numbers is much more difficult. even if we know that most real numbers are random in a way. That means that you have no algorithm allowing you to compute all their decimals.
But if, like Nicolas, you think that Nicolas Gisin, you think real numbers don't really exist as they are sort of truncated, then this will reconnect the two approaches as being the same. He has been advocating for sort of the opposite move, that is that Bohmian mechanics deep down is in fact as stochastic, because the initial condition, you know them only to say, you could even imagine that nature doesn't encode them to more than 30 digits or so, and then it's revealed. Because of chaos, very quickly, all the randomness will be as if it's revealed real time. Okay, I'm not saying I follow him here, but just to connect with you can connect that with deep views about real numbers and stuff. But I was making something simpler in a way. I've never really thought too much about this.
Okay. Other questions?
Si, il a une question. Je vais poser une question. Vous m'entendez?
Oui, bien.
Yes, so this should be in English, right? So by chance, I've already, as Antoine knows, I've already heard this talk, and I think we had a couple of technical points discussed the previous time. So maybe this time I should ask a general philosophical question to continue a little bit from Michel's question a little earlier. So let's say I believe, of course, neither in Bohm nor in collapse. Mm-hmm. And a big obstacle for me is the non-empirical surplus structure that both of them require in different ways. Mm-hmm. So philosophically, if somebody asks me to accept non-empirical surplus structure, there has to be a very good reason for paying this enormous price. Mm-hmm. And as Lev pointed out, the reasons promoted by Bohmians and by collapse people are historically slightly different. Mm-hmm. So when you tell me, guys, you have to accept non-empirical surplus structure, I say, well, in the name of what? Mm-hmm. So based on your result, how would you answer that question? Is there one universal factor in the name of which I now must accept non-empirical surplus structure? Or what's your take on that question?
So first, as a prerequisite, I'd like to say I don't believe that any of this interpretation is correct. Okay, I'm just dissatisfied with most of them. I still believe there must be that one day we will find a simpler and compelling realistic version that is compelling because it's related to maybe new laws we will find, or natural to extend the formalism, or will make sense in the same way statistical mechanics quickly made sense as an extension of thermodynamics. So I'm not really attached. I'm attached to these as sort of proofs of principle, toy models, explorations of what it could look like, what is the cost of realism, things like that. Okay, so then I've thought about it, but I'm afraid I don't have a very smart or elaborate answer to how to choose. And when will I be satisfied or such criteria? I don't know. I think it will help if something I independently worked on, if these extra structures are useful, because this is not a good argument from a logical point of view, that they don't have to be. The true, real structure of the universe could be actually not useful compared to just knowing orthodox quantum mechanics, but if we hope that we are lucky, like it could happen the same as for statistical mechanics, that this allows us to see more. I hope that this will happen, but I can't say any theory does that. There was a hope that collapse models were doing that by extending the empirical content of the theory. And what I hope to have convinced you of, at least if you believe the cheap easy inclusion, I proved that this is in fact not true if understood in the strongest sense. That is, you just disprove a certain instantiation of the theory. So it's not. I don't have the convincing. I like to know that it's possible. I like to know that there is no theorem currently saying there is no way to get realism. In fact, it's possible. It has a cost, and these toy models, I think, better than theories, chart the space of possibilities. But yeah, I'm not convinced, I hope we find something better in a way. But I still hope that this better solution will be very naively realistic, in the sense that stuff moves and that's it.
But to be fair, to answer the mission, Bernard Espagna was certainly arguing in favor of the veiled reality. But I remember him saying that the very fact that it is possible to have a realist description, such as the Bohmian description, is interesting because it proves that it is not possible to prove that there is no reality. So in a way, this is going in your direction. Even if for many other reasons, we are in this room, we are many not really believing or loving naive realism. But it's true that knowing that it's not possible to exclude that in a very strict manner, just because there are some kind of possibility like Bohmian mechanics or
yeah, I think we use different Occam's razor. So you probably have a stronger Occam's razor on the formalism, or with the kind of conceptual basis of the theory, and have a very strong Occam's razor on how naive my realism looks like. So for me, it's a very high cost to make the metaphysical picture of the universe I have complicated or less intuitive. And for you, it's a high cost to add things in the dynamics that you could not see or things like that. I think it's also what kind of priority we give to things. Yeah. But I think mostly I agree with every point you would make, and then it's a matter of taste at that stage. There is no way to conclusively.
I think that the position that we can have on the subject is not only related to quantum mechanics by itself, but also by prerequisite philosophical positions and many other things that are outside of the scope of quantum mechanics and that push people not believing in naive realism, but probably for other reasons.
Probably.
Y a-t-il d'autres questions? Nobody ask something else? Okay, so thank you very much, Antoine.